Okay, so I'm not going to go through the proofs of the fundamental theorem tonight. I'm going to, again, just postpone those. We'll do them Wednesday night or first thing on a review night. But I do want to talk about this function here. Okay? So I do expect you to understand this function. It looks intimidating. In some ways, it might be the most intimidating function some of you have looked at before. Okay? So let's see if we can suss out what's going on here. What's the variable? What's the independent variable in this function?
T.
Which one is it? How do we usually give, when we give a function and we want to describe what it's a variable of, we say f of
T or X.
x or g of x. That tells you the variable here, right? What's the variable?
X.
The variable is x. So that's the first thing you should realize. So where does x show up in the definition of the function? Where does x show up in the definition of the function? Yeah, it shows up as the upper limit of integration. You see that? Okay. So this function has a name. I'm going to call, well, f could be anything. I'm going to call g of x an area function. Okay. I do expect you to spend some time figuring out how this function works. Okay. It's pretty interesting. Okay. It's kind of a nifty little thing. So I want to give any old function. Okay, we'll call it f. Okay. So this is a function f. Now here's the difficult thing about this. I want to be talking about the area underneath the curve of f. That's what I want to describe. Okay. So where do we start measuring the area? We start measuring at A, and we stop measuring it when we get to what? Whatever the input value of the function is. So here's x, but this is fixed. I need you to think of this as being fixed, but this varies. It is the variable. So what does g of x determine? It determines the definite integral. Oops, let's do it in a different color. It determines the definite integral. Running out of colors. Let's do purple. Okay. It is the definite integral. Okay. And so notice what happens. What I want you to think of this is, I want you to think of this x as like I could slide it. I could slide it backwards. What would happen in this case to the value of g of x if I slid it to the right? What would happen to g of x? Does it get smaller? I think the total area underneath the curve, if I slid x to the right, the total area underneath the curve would increase, right? What if I slid it back to the left? It would decrease. But it would also depend upon what? This is the crux of it. What is it? That's for this case, but it depends on what?
It's greater than f.
It depends on the shape of f. It depends on the shape of f. Right? If f is increasing, then when I slide g to the right, I get, ooh, what happened there? Then when I slide x to the right, I add a lot more area. If f dips below the x-axis, and I keep sliding past that, then I start subtracting area. So the way g changes is a function or is based upon the shape of f. That realization is at the heart of the fundamental theorem of calculus. Yeah, Maria.
So is g of x just like that? Would it be just that little line that's in there? Or?
So let's say let's play with this. We'll play with it in just 1 second. I want to say one other thing about this though. Okay. So here's the thing. I could say that this is a function f of x, right? Because it doesn't matter what letter I pick for the independent variable. I could call this f of x, but if I put an x there and an x there, you would get confused. Because what is the independent variable? The upper limit of integration. That's the only x that's changing for g of x. Okay? So rather than putting f of x, we replace x with a dummy variable, sorry, t. We replace it with a dummy variable t. Okay? All right. I think based on some of the questions, and since you guys have had less time on this than my other class, let's jump straight to this area function application. Oops, where is it? Is it on here? No. It's actually on the next section. Let's go ahead and pull that up for just a moment. Okay? So if you pull up section 5.4, you got that? Sorry to make you jump back and forth. Okay? Let's take a look at, let's put this area function to work real quick. Okay? We'll do one of these together, and then I'll let you guys do the other one when we get to 5.4 officially. Mm-hmm. Yeah, I'm jumping around on you, sorry. Okay. So, we'll come back, we'll do this in detail in a little bit, but I just want to show you how this is working. Okay? I have two functions here. Okay? All along I've been saying make sure you label things. I've got two functions here. One of them is this function right here, f. Okay? F is this red function right here. Okay? As far as g is concerned, f is just this fixed function. What is the variable for g of x? Well, I just said it, doggone it. What is the variable for g? X. Which says, in this case, we're going to find the area underneath the curve between 0 and whatever x is. Okay? So we'll come back to g of 0. Let's find g of 1 real quick. What is g of 1? Well, whenever you're stuck with something, return to the definition. What is the definition of g of x? It's the definite integral evaluated from 0 to whatever x is, right? What is x in this case? 1. So we find the area underneath the curve between 0 and 1. So here we go. Well, let's see. What is this area right here? It's 2. Okay. Could you do this for all functions? No, only if I give you a nice graph that you can easily compute the area under in this case. Okay? If you don't have the fundamental theorem of calculus part 2 yet, you'd have to do it this way. Okay? So now let's find, I'd like you all to find g of 2. Okay? Find g of 2. So when I ask you to find g of 2, where do we put the 2?
On the g something.
On the x.
Okay. All right. At the upper limit of integration. All together? At the upper limit of integration. Okay. In this problem, the lower limit of integration is always fixed at 0, but the upper limit of integration varies. Okay. So what does this say? This says find the area underneath the curve of f from x equals 0 to x equals 2. So let's do that. That's what we're trying to compute. Okay. Well, we can easily do this without even knowing what f is, because it's built up of nice geometric shapes, right? So what is this area? Well certainly there's one square unit, there's another square unit, there's another one, there's another one. So I'm up to 4. And then what's left? Well, I better compute the area of this little triangle right here. Do you see that? What's the area of a triangle? Well, it's a half the base the height. Okay? So it's 1/2 the base, which is 1, times the height, which is 2. So what's the area of this part? 1. So what is g of 2? G of 2 is 5. Okay? Do you see how this works? As x changes, you just redraw the area the area underneath the curve you're looking for, and then you compute it. All right, so we'll come back to this. We'll come back to this. All right. I want to look back to this section. All right. So, what does the fundamental theorem of calculus part 1 say then? Okay. Well, it's sort of what you just realized. Okay. What's going to determine whether I'm adding area or subtracting area? What's going to determine whether I'm increasing, like as I slide to the right, whether I'm gaining a lot more area than I had before, or gaining just a little bit, or losing area, or what? The shape of f. Okay. So this is what the fundamental theorem of calculus says. Prepare to be impressed. Okay. So it says, suppose we've got any old function, f. The only requirement that we put on f is that it's continuous. Actually, we could even relax that. We could do something called piecewise continuous, but we're not going to get into that. F is continuous on the closed bounded interval. Okay? Then we could define this area function g. Okay, this is this area function. Folks, don't let your eyes glaze over. There's a lot happening in g, but where's the variable? It's the upper limit of integration. So this computes an area underneath the curve. It's a function that computes an area underneath the curve. Well, this function is also continuous. I'm not too surprised by that. Okay. It's differentiable. Ooh, that's kind of interesting. Because there's nothing that said that f had to be differentiable. F may not be differentiable. It could have cusps or corners. But g will always be differentiable. That's interesting. And here it is. The derivative of the area function is the underlying function. Yeah, that's the fundamental theorem of calculus, folks. That is the most important result from calculus.
Would that be g, the derivative of g of x equals f of t?
That's a good question. So remember, we only put the t there because we didn't want it to get confused with what x was, which was the upper limit of integration. But when I ask what is the derivative of g, it is f of x. It is the underlying function. And we said that, right? We said, what dictates how this region changes with time? Or what dictates how this region changes as we slide to the right or slide to the left? The shape of f. When I ask how is g changing, that's a statement about its derivative. So it's changing based upon the shape of f. So its rate of change is f. Okay? There's another way to write it. Okay? This is kind of a clunky, long, or it's not clunky, it's long. The other way to write it is it's a little more compact, but it's also a little more intimidating. Okay? It says that f of x is equal to d dx of the integral from a to x of f of t dt. All right. So we've just shown that any function f that is continuous on AB has an antiderivative which is g. Okay? So if I want to find the antiderivative of any function, this is how you do it. Now, that's not a very practical way of finding antiderivatives. Okay? But this says we can give the antiderivative of any function that way. Okay? All right. This next question, I went ahead and put it on here. We'll practice it some more in the 5.4. This is the classic calculus question. Okay? Everybody who writes a calculus final exam puts some version of this question up there. Okay? Because it's testing you on the fundamental theorem of calculus part 1. Okay? So, I'm asking you to take the derivative of this function right here. Is this a function? Is this thing right here a function?
Yes.
What's the variable?
X.
We're going to treat it as x. Okay? All right. What is its derivative? Its derivative just is the underlying function evaluated at x. Okay? A lot of people say, where did the t go? Well, remember, the t never went anywhere because the t was never really there, in one sense. T was the dummy variable that we used. Okay? When we start doing this, we might work one of these problems by hand with the Fundamental Theorem of Calculus Part 2, and I can show you a little bit more about what happens there. Okay? But know that in a lot of cases, this problem shows up, requires no work, and in fact, in a lot of cases, if you tried to do the work, meaning if you tried to calculate the antiderivative of this function right here by the Fundamental Theorem of Calculus Part 2, you couldn't do it. There is no nice way to write the antiderivative of this function. Okay? In fact, keep this function in mind because you could kind of follow your way through Calc 2 saying, can I find the antiderivative of this function yet? Can I find the antiderivative of this function yet? And then by the time you get to the end, you'll be able to. Okay? All right. The more practical version of the Fundamental Theorem of Calculus, and I would agree with you. I would agree with you. Okay, that's exciting, right? G prime of x equals f of x. It doesn't feel very life-altering. Okay? The more practical version of the Fundamental Theorem of Calculus is Part 2, which says if we want to evaluate this definite integral right here, as long as f is continuous, what can we do? Well, we just take any antiderivative of little f, and we evaluate it at the two endpoints. Okay? So, I think we looked at a couple of these last time. Let me just get caught up. We took the antiderivative of this function, and we said, oh, well, the antiderivative is minus x cubed plus 12x squared. And folks, I think I pointed this out last time, or if I didn't, I should have. That should have a squared on it.
It should be 6x squared.
Yes. Is it? Oh, that should be 6x squared too. Holy cow. Thank you. Okay? And this should be, again, 6x squared up there. Yep, great. Okay? Plus c, right? Because we're finding, this just says give the antiderivative. It is, so let's actually tackle this right now. I don't know if we've done this yet. Okay, so let me insert a blank page. I don't know if we've done this yet. All right. Certainly these two things aren't the same. Certainly they look similar. What is the difference? One has limits of integration, right? At first glance, one has limits of integration, one does not. Okay? These are two completely different objects. Okay? These are two. One is an animal and one is a mineral. Right? These are two completely different objects. Okay? This is a number. Right? Right?
The other one doesn't have a noun.
So let's talk about this one for just a second. This says we take f of x and we calculate what? The area underneath the curve of f of x from a to b. What should that return to us? A number. Okay? It is absolutely critical that when you look at this, you see a number. Just like if I say f of x, let's not do f, just like if I say h of x is equal to x cubed minus 16x plus 7, then you should be able to look at h of 3 and say, what's h of 3? It's a number. Same thing. This is a number. Specifically, it's an area. But area is given as a quantity. Okay? What is this up here?
A line.
It's a function. I'll take that. That's close enough. Okay? I'd rather you say that it's a family of functions. It's a family of functions. Why? Because we always give it with that plus c on it, right? So there's many functions that satisfy the fact that if you took the derivative of one of them, you'd get f of x. Okay? So one of these is a function, one of these is a number. This to me sort of reminds me of what is f prime of x? It's a function. What is f prime of 3? It's a slope of a tangent line. Okay? That's kind of the same idea here. So going forward, it is absolutely essential that you see these two as two related animals, or two related entities. They both have this curly s thing. Okay, we've talked a little bit about how they're connected. Okay. But it is also essential that you understand they're different, not just like, oh, one doesn't have any limits, okay, but one is a number and one is a function. Okay. All right. So, we just gave the family of functions that satisfies the criteria that their derivative is negative 3x squared plus 12x. Okay? All right. Then I said pick an antiderivative so that the c is equal to 0. So let's just say that. That'd be x cubed plus 6x squared. In this procedure, we're about to start practicing using the fundamental theorem of calculus part 2. And in this procedure, we always pick the constant to be 0. Just because it makes the calculation a little bit simpler. You don't have to do that. You could buck the trend. Okay, but it's silly to. Okay? All right. So, how do we work this? Okay. Well, if you were the cat's meow and somebody said calculate this, what did we have? Negative 3x squared plus 12x. Don't write this down. If you were the cat's meow, then in one step you could do this. Okay? In one step you could say that's negative 2 cubed plus 6 times 2 squared minus parentheses negative 0 cubed plus 6 times 0 squared. Okay? But what's hard about that? It's way too many steps to do in one move. Why? Because I was taking the antiderivative and evaluating it in the same step. Okay? So we never do this. People make way too many mistakes if they try. Okay? And I only felt comfortable even remotely trying it because I was actually looking at the antiderivative up there. Okay? So what do? Well, we give the antiderivative, minus x cubed plus 6x squared, an antiderivative, but then we remind ourselves that we were supposed to evaluate it at the upper and lower endpoints. So that's what that notation means. 2, thank you. Okay. So what do you do with this notation? How do you interpret this? This says, first take this expression and evaluate it at 2, and then put a minus sign, and then take this expression and evaluate it at 0. That's what that's a shortcut for. Okay? So this is equal to negative 2 cubed plus 6 times 2 squared minus parentheses negative 0 cubed plus 6 times 0 squared, which is equal to
Negative 8 plus 24 minus 0.
negative 8 plus 24 minus 0, which gives us 16. What did we just show? Okay. Well, we were asked to find what? We were asked to find that number right there that represents the area beneath the curve, right? We were asked to find that area right there. how did we go about actually finding that area? We went to the antiderivative, and then what did we do? We plugged in a 2. We got out the value 16, and then we plugged in a 0, and we got out 0, and then we looked at the difference in the two y values. What's the difference between the two? Well, it was 16 minus 0, which equals 16. Okay. By the way, I had somebody make this observation in my other class, and I don't think I could have said it better. He said, oh, you just took a two-dimensional problem and turned it into a one-dimensional problem. The question was about calculating area. We looked at distances on a line. Okay? Going forward, that is like, so if you think of calculus as a nice, award-winning season, a television or something, we're in the first, this is the final episode of the first, I'm losing my metaphor, final episode of the first season, but here's some hints as to what's coming. Okay? These questions right here, they'll get answered in Calc 3. Okay? All right. All right. All right. I'd like you all to try letter C now. There's no graph, but you don't need a graph for any of these problems. Try letter C. Okay, folks, let's take a look at this. Okay? So, let's keep practicing our vocabulary. Okay? This symbol right here is called the what? Well, all of it together is called the definite integral, right? Okay, this symbol doesn't have much of it's not a very fun name. The symbol's called the integral sign. Okay? The integral symbol. Okay? What do we call k of x if it's in the context of sitting inside of the integral symbol? It's the integrand. That's pretty bad, folks. What's it called? It's called the integrand. Okay? What's my lower limit of integration? Okay, what would I call 3? Yeah, you guys got to keep working at it. Keep working at it. Okay? Do talk math aloud to yourself. Okay? All right, so let's go ahead and substitute in what k is. Okay? Now what do I do? Well, I could return all the way back to the limit definition of the definite integral that involves the limit of the Riemann sum. You do that in 5.2. It's a good exercise. Okay? Kind of a little bit of hazing. Okay? Before you get your calculus badge. Okay? But now what do? Generally, we always go to the fundamental theorem of calculus part 2, and we go ahead and give an antiderivative of this function. What's an antiderivative of it? Evaluated from x equals -3 to x equals 3. That negative looks horrible. -3. How are we doing? Okay. Folks, I do want you to have these strings of connecting equal signs and stuff. Okay? I got too many is still just giving me marks on a page, and whenever I see that, I put your test at the bottom and I go grade somebody else's. James. So I'm going to be really precise with the language, and then you don't have to worry about being this precise. Okay? We didn't find the antiderivative, we found an antiderivative. Specifically, we chose an antiderivative with our c value being 0. Yeah. So you don't. So, I mean, sort of the loosey-goosey way of saying it is, this needs a plus c, this does not. Okay. Yeah. So this gives us 1/4 times 3 cubed minus 2 times. Oops. 1/4 times 3 to the what? 1/4 times 3 to the 4th minus 2 times 3 squared minus 1/4 times negative 3 to the 4th minus 2 times negative 3 squared, which equals 0. Wait, 0? Does that bother you?
Because it's the net.
It's the distance.
The net area, bro.
So picture what's going on here. Picture what's going on here is I have this function right here. I think it looks something like this. And I just asked you to compute the area between here and here underneath the curve. Will this always happen?
Not always.
No. Okay. Two things were happening. Two things were happening. One, the limits of integration were equal and opposite. And two, the original function, now careful, did I just draw f or the antiderivative of f? That's f. Okay. F was an odd function, which means that what's happening on one side in the first quadrant is happening also in the third quadrant. There's that symmetry about the point 0, 0. Sorry, I didn't quite go through there. A little better. Okay? So you can see that if you said, okay, well, let's find this area, and this area, and this area, and this area, because we're taking a definite integral which computes the net area, then we have negative regions, and the negative regions precisely cancel out the positive regions.
That's symmetric.
Because of the symmetry that's due to the fact that f was an odd function to begin with. All right. Okay, I'd like you to do D and E and F. Do all the rest of this page.
You just become. Thanks.
Oops. Come on here. Here I'm asking you to find the derivative of this function. Well, its derivative would be the first times the derivative of the second plus the second times the derivative of the first, and then minus e to the x for the derivative of that second term there. Oops. Times 1 minus e to the x. When you clean up everything, what do you get? X e to the x. What is the derivative of this function? X e to the x. Okay, one more time. What is the derivative of this function? X e to the x. So, what is the antiderivative of this function? This one. Okay? That's all right. That's all right. Okay, you're learning. I used to do that in my Algebra 1 class. I would ask them to first expand a binomial. They'd get an answer, then I'd ask them to factor that binomial.
That's me.
Right.
That was kind of mean, I guess. All right. So, folks, the reason why I do this, and this is I do give you this for two reasons. One, because I do want you to learn how to see the forest through the trees, or whatever. Okay. But the other thing is try as you might, I don't think you can just think of the antiderivative of this function. Try as you might, I don't think you can just call upon your knowledge and say the antiderivative of x e to the x is blank. Okay? And in fact, you'll need some very specific tools in Calc 2 to be able to take this antiderivative. It may be one actually, you might do it in the first 2 weeks of Calc 2, but you need a very specific procedure that I doubt many of you have seen before. Okay? Doesn't matter though. Doesn't matter if I can't by brute force take the antiderivative of this, because in the problem above I said the derivative of x e to the x minus e to the x is x e to the x. So by the fundamental theorem of calculus, I give this antiderivative, which is x e to the x minus e to the x, evaluated from -2 to 1. Okay. Does anyone have any questions about what we just did there? I'm all fired up, but I'll calm down. Any questions on that? Okay. So, now that we actually do this, so we get 1 e to the 1 minus e to the 1 minus parentheses -2 e to the -2 minus e to the minus 2, which gives us 0 plus 2e to the minus 2 plus e to the minus 2, which gives us 3e to the minus 2, or if you like, 3 over e squared. And I don't care.
3 over e squared?
You can give yourself a decimal approximation of that if you want, but I'm interested in the exact answer here. Watch your negatives, though.
Negatives come from.
Yeah, we got to watch the negatives, right? So this is our lower limit of integration, so it gets a -2. Okay. Where did this minus sign come from? That minus sign came from the fundamental theorem of calculus part 2. Okay. That's because, remember, the fundamental theorem says you take capital F of B minus capital F of A, which is what all of this is right here. Okay. I guess I should be using a G, but I'm not going to.
Well, so that becomes positive 2 over e squared, right?
Sure.
On the first part on the right side.
Sure, if you want.
Minus still, though.
Minus a minus.
Oh, you distribute that.
All right.
Yeah, that's right.
Folks, here's another opportunity. I was trying to find this earlier when somebody asked the question about how to use the area function. I should have scrolled down further. Okay? Let's practice using this area function. Okay? I'm asked to find a of 2 here, folks. Don't let your eyes glaze over. If you get stuck on something, don't try to answer it all the way through. Just do the most basic step you can. What does it mean to evaluate a function at 2? Plug in 2 everywhere you see an x. So let's do that. That's the integral from 0 to 2 of f of t dt. Okay, folks. I often spend a lot of time writing maybe more work than I have to, but because I know that eventually I'll get to a problem that I don't know how to do. And by showing myself little baby steps like this one right here, now this problem's straightforward. What does this say to do? It says find the area underneath the curve of f of t from x equals 0 to x equals 2. It's given to us. Right? Okay. All right, do the rest of them. I'd like to do Roman numeral 2 here. You can do this in much less work than I'm about to do. I'm going to put some extra steps in here. You don't have to add them, but I think it'll just be good to see in class. So this is the integral from 0 to what?
0 to 5.
0 to 5 of f of t dt. Okay? Folks, if you are hesitating writing this symbol because you don't feel comfortable with it, then you need to write it more. Okay? All right. I'm going to break this up as the integral from 0 to 2 of f of t dt plus the integral from 2 to 5 of f of t dt. Is that a legal move?
Yes.
What are we doing here? We're adding up infinitely many rectangles, right? We're adding up an arbitrarily large number of rectangles from 0 to 5. So what did I do? Well, I first added them up from 0 to 2, and then from 2 to 5, and then I combined the results together. Right? So if I asked you to find the area, of a big room, you could find the area of little pieces of it and combine them together. Okay? I'm sorry, this is hard to see. I'm just working on number 5 here. Yep.
Okay, sorry.
Yep, and I'm going to erase it in just a moment. But what was this answer? This answer was 8. And then what does this say? It says evaluate the definite integral. So that returns -3. Oh, excuse me, negative 5. And so we get that the answer is 3. Okay? Okay, folks, I am completely comfortable putting this up here because I completely understand this notation. As you're making notes to yourself, showing more work in the beginning is probably more beneficial than showing less work. Okay, all right. Let's see, we get -8 here? Okay. Now, let's look at, sorry folks, my numbering system got all goobered. This should be 4, 5, and 6. Okay?
Instead of 4, 4, and 4. Bow, bow, bow.
Yep. All right, h of 8. Folks, let's write it out. H of 8 is the integral from what to what?
2 to 8.
From 2 to 8. Did everyone catch that little 2 down there?
Yes.
Did.
Okay. This would be of f of t dt. So what is this? I'm not going to be quite as pedantic here. We go, that's -5. I get -16. Okay. I do want to write this one out as well, folks, because it's one of the properties we discussed. What is the integral from 2 to 2 of f of t dt?
0.
It's got to be 0, always. What's the area of an infinitely thin line? 0. Okay. All right, h of 0. Folks, I want to work through this one. H of 0, the integral from 2 to 0 of f of t dt. You are welcome to rationalize your way through that however you wish. I'd like to use one of the properties that we gave last time, though. I'm not used to my limits of integration going this way. I'm used to reading them from left to right as well as up to down, right? So let's swap them. Can I swap them?
Yes.
Yes.
I can. Can I swap them without consequence?
No.
No. So let's swap them,
We have to pull out a negative.
but now we got to pay for it. And we put a negative there. Okay? You can interchange the limits of integration provided you change the sign on the outcome. Okay? There's lots of ways to rationalize your way through that one, folks. Okay, what do we get? We get -8.
Slaves. You do get -8?
Yep.
Even though the graph shows 8.
So the graph shows from 0 to 2,
Right.
but you're going from 2 to 0. So you're going backwards. You're decreasing.
Moving
So you're moving negative.
I thought you were like 0 and walking.
One way to see it is notice that all of our delta x quantities, if we were to do this, chop this up, all of our delta x's would have a negative sign. And those would go all the way through the whole procedure and come out
Okay.
right there.
Righteous.
All right, folks. One of the things you want to get good at with integration is knowing when you got to be careful and when you can sort of proceed blindly through the problems. Okay? All right, let's do this. Here I'm asking you to find the net area underneath the curve, sine of x, from x equals 0 to x equals 5 pi over 4. This is the integral from 0 to 5 pi over 4 of the sine of x dx. Okay? I'm asked for net area. That is just the definite integral. So what do? Well, I give myself an antiderivative. I like that one right there. I think you should too. Okay? Evaluated from x equals 0 to x equals 5 pi over 4. This is equal to, watch those negatives. This is equal to negative cosine of 5 pi over 4 minus, where'd that minus sign come from?
The
From the fundamental theorem.
whatever you want to call it.
Minus the cosine of 0. This is equal to minus square root of 2 over 2 minus a minus 1, which is equal to 1 plus radical 2 over 2.
I just flip them, just-
Yeah, I don't know.
Oh,
I
okay.
like to lead with integers.
2 root
Okay.
over 2.
Square root of 2 over 2.
Yeah, the one.
Oh, you could write it as 2 plus radical 2 all over 2. Yeah,
Two,
sure.
yeah, so it's-
Yep.
yeah.
That, and in fact, my
That's
math
what I
lab
was
would probably want you to write it that way.
Yeah.
Yeah. Questions on that, folks?
Bonus.
All right. Graphically, what did we just do? Graphically, we just computed this net area right there. Right? That's what we were asked to do. But in practice, what did we actually do?
On the distance.
Yeah, we found the distance between here. What's that order pair? That's the order pair 0, -1. And this order pair right here, what's that order pair? That's the order pair 5 pi over 4. 5 pi over 4, comma, radical 2 over 2. And then we said, what is the distance between this point and this point? Okay. Folks, I'm really spending a lot of time on these early graphs because pretty soon they will all be in the background and you won't see them at all. Okay, so it's really important that you spend some extra time right now and develop some intuition between this expression right here, which means this, and how we actually compute it, which is by looking at this distance right here. All right. What is the difference between 10 and 11?
To find the total area, you add them.
Yeah, so for the total area, we want to count all of the region's areas as positive. Yeah. Okay. I'm going to do this twice, folks. Okay. The first time through, I'm going to do it how I would normally do it, skipping some steps, and then I'll come back and we'll fill them in. Okay. If I were doing this problem on my own, okay. First of all, why did I put the absolute value on there?
Because you're calculating the total area.
We want the total area. Okay. If I were doing this problem on my own, this is what I would write. Okay. So I would write this as the integral from 0 to pi of the sine of x dx minus the integral from pi to 5 pi over 4 of sine of x dx. Okay? That's how I would do this one, having done these problems many, many times. So eventually you'd want to write it this way. Okay? Now, there is one thing I think we should all see right away. Why did I choose to break this up at pi? That's where the graph of the sine function changes sign. That's the only place on this interval where it changed sign. What if it changed signs multiple times on that interval? What do you say, Austin? What if it changed multiple times on that interval? Either one. Austin, listen.
You would have multiple things.
So we'd have to break up the interval for every time it changed sign.
Couldn't we do a sum, like a summation on that, pretty much?
Well, not really, because the limits of integration are different,
Yeah, that's true.
right? So I
There's
mean,
no way to notate that?
there probably is, but it's probably harder than actually just doing it. I won't have you do a problem where it crosses the axis 30 times in an interval. Yeah, but it might cross 2 or 3 times. That's fair game. Okay, so let's actually do the work here to arrive at what I just wrote. Okay, so we see now that we want to break it up at 0 from 0 to pi, and then again from pi to 5 pi over 4. Okay, that should make sense. All we've done is broken it up at the place where it changed sign. Okay? Now, to somebody standing at the door looking in, they'd say, "Oh, he just dropped the absolute values. He didn't like them, so he made them go away." You never ever just wish away absolute values. You always have to go back to the definition of absolute values, right? Okay. Well, the absolute value has a 2-part definition. It says if the expression's positive, what do?
Leave it alone.
Leave it alone. If the expression's negative, what do?
Negative.
Change the sign. Okay? And I would prefer if you think of it that way. Some people say you make it positive, but I don't like that phrasing. I think it gets you into trouble. The absolute value of a positive number is just that number. The absolute value of a negative number, you change the sign on that number. Okay? So here we go. Well, for my first interval, what do we notice about the sign value?
Positive.
It's always positive. So if I want to take the absolute value of the sine function on that interval, I just leave it alone as sine. Okay. But what about this second one? So it's always negative, so I change the sign on it. That's a S there. It looks kind of funny. We okay with that? But of course, now you can see where I got what I initially wrote, because what could I do with that negative number if I wanted?
Pull it out of the
I could just pull it out. Okay? So what I've learned to do is just break up the function where it crosses the axis. If it ever dips below the axis, I just stick a negative sign in front of it to change the sign on it. Okay? You're welcome to do that however you wish. Okay? But that's the way that makes the most sense to me. Okay? All right. Let's go. I'll go ahead and keep writing this out. So let's see here. This would be this would be minus cosine of x from 0 to pi. Let's see. I guess I'll work with what I'm working with here. So this would be plus the cosine of x times the integral from pi to 5 pi over 4. Folks, I'm just finishing this out and I don't have enough room to. Are there any questions about what I just did there? Folks, how many points would you award problem number 11 if you were writing your own exam? How many points would it be worth? 11?
No, just kidding. Like 5.
5? Maybe 6? 4? Between 5, 6, and 5 and 6 points? 4, 5, and 6 points?
Just 5.
5, great.
5.
How many points do you think I allot you for crunching numbers? 1, maybe 2, probably 1. Okay? So, if I were you guys, and if I were a student, okay, I would do my test questions up to here, and then I would move on and do some other work. Because what is this? This is crunching a number. What are you going to do? You're going to get it right or you're going to get it wrong. You're either going to get 1 point or no points at this right near here, right? And if you want to get even closer, look at this. Just go ahead and plug in, there's minus cosine of pi, minus parentheses, minus cosine of 0, plus cosine of 5 pi over 4, minus the cosine of pi. Now you're even closer to the right answer. Okay? I've had students, and not on sometimes on a test, sometimes in their homework, spend 20 minutes trying to remember how to simplify all of this. Okay? I don't think that 20 minutes is worth your time at this point in the semester. Okay? Please, 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 I'm not saying it's not important. I'm saying if you still haven't learned all the other material, and you're spending 20 minutes trying to simplify this expression, you're spending time, you could spend your time better, is what I'm trying to say. Okay, does everyone understand? Okay. Certainly this is important, but it's not as important as understanding the material. And to me, you know, I expect you to know what your trig functions are, but boy, we all make mistakes. If you make a mistake, -1. Okay, move on. All right. Now again, I'm not saying don't do it at all, but if I were sitting in your shoes and I get to here, I'd say, all right, now I'm going to work on another problem. If I get all the way through the test, I'll come back and evaluate those. Okay? All right.